Good morning, students. Myself, Vaidegi, working as assistant professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject Analog IC Design for 6th semester ECE students. First, see why we are using differential and cascade amplifiers. Let's start by understanding why we even need differential and cascade amplifiers. Each plays a distinct yet complementary role in improving circuit performance. Differential amplifiers are workhorses for handling noise. By amplifying the difference between two input signals and rejecting common noise that appears on both, they significantly improve signal integrity. This is vital in environments where signals are prone to interference. Cascade stages, on the other hand, are all about enhancing the fundamental characteristics of an amplifier, gain and bandwidth. They achieve this primarily by reducing the dreaded Miller effect, which limits bandwidth, and by increasing the amplifier's output impedance. This gives us more control and better performance characteristics. When you combine these two, you get a powerful combination. Together, they form the backbone of high performance analog front ends found in critical devices like analog to digital converters, precision filters, and communication systems. They are essential in achieving high accuracy and speed. Next, we see about the key specifications to balance. When designing these amplifiers, we are always performing a balancing act with several key specifications. First, the slew rate. This defines how quickly the output voltage can change. If your signals are fast, your slew rate must be high enough to follow those changes without distortion. It's often a limiting factor for high speed operation. Next, noise. We always wanted to minimize input preferred noise to maintain signal integrity. Poor noise performance can mask your actual signal, especially when dealing with very small signal voltages. Then we have gain and bandwidth. Ideally, we want a high DC gain for strong amplification and a wide bandwidth to handle a broad band range of frequencies. Achieving both simultaneously can be challenging, requiring careful design choices. Input common mode range is crucial for reliability. It ensures that your input signals stay within the linear operating range of the amplifier, preventing clipping or non-linear behavior. Finally, the power dissipation and voltage swing. We need to design for efficiency, minimizing power consumption, while also ensuring the amplifier can produce the maximum output amplitude without distortion. These two are often at odds, requiring careful trade-offs. Next, we see about the differential amplifiers. This basic structure is designed to amplify the difference between two input signals. Think of it as subtracting the common noise while magnifying the signal itself. This is incredibly effective for signal integrity in noise environments, as unwanted common mode signals are largely rejected. When we talk about design parameters, we are looking at the things like the desired gain level, ensuring a low noise performance specific to the differential input, achieving adequate bandwidth, and critically a high common mode rejection ratio or CMRR. This ratio tells us how well it rejects those common mode signals. This requires a meticulous selection of transistors and precise biasing techniques to ensure balanced operation. Their applications are widespread. You will find them in instrumentation where precise measurements are key, in audio processing for clean sound, and in sensor signal conditioning where tiny sensor outputs need to be reliably amplified and stripped of interference. Accuracy and stability are paramount here, and differential amplifiers deliver. Next, we see about the cascade amplifiers. Their configuration benefits are significant. The cascade stage enhances both gain and bandwidth, and importantly, it dramatically improves the output impedance. This makes them a fantastic choice for high frequency applications where loading effects and Miller capacitance can otherwise degrade performance. However, like all engineering decisions, there are trade offs. Designers must carefully navigate things like voltage swing limitations, higher power consumption compared to simpler configurations, and managing noise performance. This often demands innovative biasing techniques to optimize the circuit for a specific set of performance goals. Cascode amplifiers are widely used. You will see them in RF applications. For example, in the input stages of receivers in video processing, where high bandwidth is essential, and in precision analog systems. They excel in scenarios that demand high gain with minimal signal distortion across a wide frequency range. Next, see about the cascode design implementation. Here we see a typical cascode design implementation while the specific circuit may vary. The core idea is to stack two transistors, often a common source or common emitter amplifier followed by a common gate or common base stage. The beauty of this configuration is how the upper transistor, the common gate stage, effectively shields the lower transistor's drain. This reduces the voltage swing at the drain of the input transistor, which in turn drastically reduces its Miller capacitance and leading to a much wider bandwidth. It also presents a higher output impedance and giving us more gain. We will often see its implemented design with MOSFETs or BJTs, and the key is to ensure proper biasing to set the operating points for optimal performance across voltage and current. Next, we see about the design consideration. Stepping back a bit, let's reiterate some overarching design considerations for both these amplifier types. Slew rate, as mentioned, is paramount. You must have low slew rate to handle the fastest transitions of your input signals without distorting the waveform. This means carefully balancing speed with power consumption and overall bandwidth. You can't just crank it up with consequences. Noise performance, another critical aspect. Minimizing noise means careful transistor selection considering their intrinsic noise characteristics and meticulous layout design. This is especially true in sensitive applications like medical devices, where even tiny amounts of noise can obscure vital signals. Finally, the gain settings. To achieve high gain, we must often employ feedback mechanisms which stabilizes the gain and reduce distortion. We also look at specific transistor configurations like cascoding, which, as we discussed, can significantly influence and boost the overall gain and capabilities of your amplifier. Next, we see about the advanced cascode topologies. Building on the basic cascode, engineers have developed advanced cascode topologies to further optimize performance for specific applications. This can include folding cascodes, which allow for a larger output swing by shifting current paths, or regulated cascodes, which use feedback or further increase output impedance and improve power supply rejection. The goal with these advanced topologies is often to push the boundaries of gain, bandwidth, and output swing, or to reduce power consumption, while still leveraging the fundamental advantages of the cascode configuration. It shows the incredible flexibility and adaptability of analog circuit design. Next, we see about the high gain techniques. Achieving high gain is a common requirement, and there are several general techniques we employ beyond just the base design. One straightforward design is stacking stages. By connecting multiple amplifier stages in series, you can achieve incredibly high volt overall gain. The challenge here is ensuring that coupling between stages is effective and the feedback techniques are properly implemented to maintain stability, bandwidth, and slew rate across the multiple stages. Feedback mechanisms, particularly negative feedback, are incredibly powerful. They can stabilize the gain, making it less dependent on component variations, and dramatically reduce distortion. This also often improves linearity and the overall frequency response on counteracting any non-linear characteristics of the amplifier's open loop gain. However, all these techniques involve trade-offs and optimization. We are continuously working to optimize component values and their arrangements. The goal is to enhance gain without introducing problems like thermal instability or excessive power dissipation, which can lead to overheating and reduce reliability. Next, we see about the performance verification and specifications. Once we have designed and built these amplifiers, a rigorous performance verification and specifications are absolutely critical. This involves extensive testing to ensure that the actual amplifier circuit meets all the target specifications we have discussed: slew rate, noise figure, gain, bandwidth, common mode rejection, power dissipation, and so on. We use specialized equipment like oscilloscope, spectrum analyzer, and a network analyzer to characterize the circuit. We verify its behavior under various operating conditions, different temperatures, supply voltages, and load conditions to ensure robustness and reliability in the field. This step is where the rubber meets the road, confirming our design performance as intended. Finally, we came to the summary of this lecture. The design of different cascade amplifiers demands an integral design approach. Looking ahead, we can anticipate exciting future trends as fabrication technology advances. We are seeing greater integration of components at ever smaller scales. Ultimately, continuous innovation defines analog IC design. It is a fertile area for ongoing evolution, particularly as the demands for high performance, greater efficiency, and miniaturization continue to grow across virtually every industry from consumer electronics to advanced scientific instruments. Thank you.